Good afternoon, young people. Today we're going to be talking about chemical reactions and equations. We're really just going to go over the vocabulary and the basics so that we have an understanding as we go through and we're talking about this, what we're talking about, what we're trying to express, okay? So, recognizing chemical reactions. First of all, we are using equations to represent reactions. How do we recognize that a chemical reaction has occurred? Well, chemical reaction is a process in which one or more substances are changed into new substances. You're like, new substances, what does that mean? Well, new substances mean that they're different. They don't have the same properties. They don't show the same things. We're not getting the same stuff when we're finished. New simply means the substances that were not there before the reaction. So how do we recognize when that's happening? So how do we know when a chemical reaction has occurred? There are several factors that identify this. First factor, energy is given off as heat or light. Second one is gas is formed. The third one is a precipitate or a solid settles on the bottom of the container. The fourth one is a change in color, a change in odor, or a change in temperature. Wow, it's repeating itself. Okay, so in general, these are the six. 1, 2, 3, 4, 5, 6 that we see. I'm going to show you something really quickly because I want to make sure that we have an understanding. This one, this one, this one, and this one are sure things. If you see any of the 4 that are checked off, you definitely have a chemical change. These 2, on the other hand, yeah, you have to have one of the others. So if you see a change in temperature or a change in odor, you have to also see one of these other 4, okay? If you don't see one of the other 4, then you don't know that you have a chemical change. It could be a physical change. Excuse me. So make sure that you have seen the 4 and you know that the 4 that are checked are for sures. If I see heat or light given off, it's a chemical reaction. If I see bubbling, a gas is produced, it's a chemical reaction. If I see a solid being produced where there was no solid, it's a chemical reaction. And if I see a change in color that wasn't there before, it's a chemical reaction. If I just smell a change, nah, maybe not. I got to have one of the other 4. If I feel a difference in temperature, got to be careful. I have to have one of the other 4. So when I see the bottom 2, I have to have one of the other 4 that go along with it. So just be really careful about that. Okay, so next up, chemical equations. So we need to talk about the words that describe chemical equations and what that means. So a chemical reaction cannot be seen. It occurs on what we call a nanoscopic level. That means at an atomic level, submicroscopic. We can't see it. We can't even see it with a microscope. That's why it's submicroscopic, or we call it nanoscopic. So instead of trying to worry about the fact that we can't see it, we write what we call a chemical equation that is representative of what we see happening in the chemical reaction. So a chemical equation is a written expression that illustrates a chemical change or a chemical reaction. That's all it is. It's a sentence, basically. And there are going to be different formats for that sentence that we're going to see in just a minute. All chemical equations have 3 basic parts. The 3 basic parts are simply this. We have our yield sign. It's the equal sign. And then we have reactants on this side and products on this side. So those are the 3 basic parts. So what does that mean? Reactants are one or more substances that you start with. So they're the starting materials. If I have more than one, I use a plus sign to separate them. The yield sign, or the arrow, is an equal sign for us. And we'll learn how that's equal in just a few minutes or a little bit later. And then finally, products are the new substances that we've formed. If there's more than one new substance, we use a plus sign to separate it. So 3 parts: reactants, products, and the yield sign. That's what we have. Okay? So types of equations. There are essentially 3 types of equations that we could see or have. So the first type is a word equation. A word equation is basically a written expression of the chemical reaction, and it involves a sentence. It's all words. We haven't anything else. We talk about the chemical reaction in a word as if we would write it in an English class. So an example of this is potassium metal reacts with oxygen gas to produce solid potassium oxide. This is a word equation. It's pretty simple, pretty straightforward. It has all of the information we need to tell the type of phase it's in. It tells us what are reactants. It tells us what are products. Usually things like to produce, to react, forms, makes. All of those words tell me, hey, that's the yield sign. That's what I'm equaling. I'm going to have what I made. So that's how a word equation works. Second type of equation that we can have is a skeletal equation. Skeletal equations are written to give us a shorthand version of the word equation. But actually, the shorthand version is a better equation for us overall. So what is an example of that? An example of that is Mg plus S yields MgS. Pretty simple. Okay? So we're using the symbols. Now, I would include a couple of things here. I would make sure that I included the state, so I'd probably put in solid and solid. I'm probably going to need heat to make this reaction happen, and I'm probably going to get a solid here. Okay, and we'll talk about all those symbols in just a minute. Okay? All right, last type of equation. The law of conservation of matter states that matter cannot be created or destroyed, very much like energy. Okay, so that means that on a nanoscopic level, we have to account for all of the atoms. That means if we have an element on the reactant side, that element better show up on the product side. But it goes further than that. We not only have to have the same elements on both sides, we also have to have the same number of atoms on both sides. And so that leads us to the next type of equation that we need to talk about, balanced equations. They're written using chemical symbols and formulas, but they also follow the law of conservation of matter. That means I have equal numbers of atoms on both sides. So an example is here, 2H2O plus O2 gas yields 2H2O gas. And what I see here is I see numbers right here and here. We call those coefficients. Those coefficients tell me how many H2s I need to get the same number of atoms of H2 on both sides. So according to this, I need 2 H2 molecules to get the same number of hydrogen atoms on both sides of the equation. Okay, I've got 2 H2O, so I've got 4 here and 4 here. Notice I don't have a number right here and written in front of. Well, just like in algebra, when we have X, when there's nothing there, it's 1. So there's one O2 molecule, and that makes sense because that means one O2 molecule is 2 O's. There are 2 H2O's, so 2 times O is 2, so they're equal numbers. So balancing involves having equal numbers on both sides. All equations must eventually be balanced. We have learned, and we will learn at first, this idea of word equations going to skeletal equations and identifying types of reactions. But then next piece will be adding on balancing. We will add on the idea that we need to make sure atoms are the same. I first want to introduce the idea of chemical reactions as basically ways to write down what happens in a chemical change or a chemical reaction. Chemical equations are ways to write down what happens in a chemical reaction, okay? So I hope we're feeling better about that, all right? So writing chemical equations, there are some abbreviations that we use, some things that we need to make sure that we're aware of. First of all, this arrow is a yield sign. It divides reactants from products. It's very similar to an equal sign, okay? Then we have pluses. Pluses go between multiple reactants or products. So if we have more than one reactant, we have a plus between them. If we have more than one product, we have a plus between them. The Greek letter delta, or the triangle, indicates that we've added heat to make the reaction happen. That doesn't mean a combustion reaction. Typically, I have to start it, but I don't have to add heat to get it to go and finish. I'm talking about when I put something into a test tube or into a dish and I heat it, like with a Bunsen burner. I have to add heat to get that to happen, okay? I means that I am not adding heat. I'm sorry, that's a mistype, that's a typo. I'm electrocuting, or I'm adding electricity to make that equation happen. Electricity needs to be added. And then finally, chemical formula. Well, if I have a chemical formula above, written above there, then that indicates that I'm using a catalyst, something that's going to help the reaction go in a different way. And then, of course, we see S in parentheses behind things. That means things are in solid state. L means things are in liquid state. G means things are in gaseous state. And AQ means it's a mixture. It's something dissolved in water. So when we see AQ, it's a mixture. When we see solid, liquid, or gas, it's a pure substance. So these things are pure substances. This one is a mixture. We need to make sure that we remember that. So writing a chemical equation. So we start with a word equation. Example, propane tricarbon octahydride gas reacts with oxygen gas to form carbon dioxide and water vapor. First, we want to change those words to formulas using abbreviations. So we basically write the chemical formulas, and you can see what we've done. Propane tricarbon octahydride, there it is. Reacts with oxygen gas, there it is. Remember, oxygen is part of Brinkelhoff, so we have to have O2 because it never occurs by itself. And then we see the words to form. Well, to form means the yield sign, okay? Then we have carbon dioxide gas, there we go, carbon dioxide gas, and water vapor. Vapor means water is in gaseous form. We use that to describe water. So that is getting to the skeletal equation. So what does a balanced equation look like of the same thing? Okay, notice it says you're going to learn how to do this later. We will. We're going to learn how to do it later. Don't panic if you don't know. I want to introduce a little something here. So we've balanced the equation. You notice coefficients 1, 5, 3, 4. Those are the things that we have to multiply each of those things by to make sure that all the carbons are the same on both sides, all the hydrogens are the same on both sides, and all the oxygens are the same. That doesn't mean carbon, hydrogen, and oxygen have to be the same. That means carbon is the same on both sides. Hydrogen is the same on both sides. So remember, we are going to be picking this up later, so I don't want you to panic about this. This is just the introduction of vocabulary. Thank you.